Okay, let's continue. Last part 12, we ended at the point we talked about the ionic bonding. Ionic bond was defined as the electron pair, which we call the bonding electron, is coming from the electron completely transferred, most of the case, from the electropositive element to the electronegative element in the periodic table. Mainly we'll talk about the metal elements, their atoms losing electron completely, we call transfer, to the non-metal elements on the other side of the periodic table and belong to electronegative elements. Then the electron transfer was kind of complete, we consider, and then one side, which is metal elements, they lose their atoms, lose electron completely to the non-metal elements, their atoms, and then the form of bonding because the electron fitting to their electron configuration to result more stable situation, so form a more stable compound in nature, and that is called ionic compound with ionic bonding, right? The electron transfer. So if we look into the relationship between the electronegativity value for those elements involved ionic compound, for instance, we talk about the table salt, right, NaCl, and the NaCl, sodium as a cation from the metal lose electron, the one at the very far outside, outskirt, the suborbital, and the electron either to get lost or stolen by the electronegative elements. Chlorine has a stronger affinity towards the electron. That's where we talk about electronegativity, right? The affinity towards the electron during the bonding formation process. So the chlorine atom has a high tendency to pull the electron towards itself, right? And putting to its half-filled, all right, 3p orbital, I think either px, py, pz, doesn't matter, because it's degenerated as the same, identical in the space. It has 5 electrons left off from the p block in the chlorine gas situation, and then that will be filled up by the electron from the sodium. So form a single bond. Now the difference between the electronegativity value for those elements is very, very clear. For the electronegativity for sodium, Chi Na is 0.9, for Chi Cl 3.0, for chlorine, 0.9 here and 3.0 there. And the difference between delta Chi is 2.1. Now that value fitting to the criterion for judging if the bond is ionic or not, that's exactly where it starts. If the difference between electronegativity is larger than 2, it's going to be ionic. It could be even bigger than 2, right? And but if it's lower than 1 or equal than 1, equal and lower than 1, that will be covalent. Now we already talked about compounds. We involve the binary compound, either ionic binary compound or a covalent binary compound. Now let's talk about binary compound with covalent bond, right? The second category for the bonding type in relation to the electronegativity. Now what is the covalent bond? It's defined as by forming the bonding by sharing the bonding electrons. How many? 2 electrons, right? One with self-spin clockwise, the other one with self-spin counterclockwise, made from different nuclei from 2 different elements, right? In this case, these 2 electron form bonding. Those electrons is not going to extreme one nucleus for one element or stay with this side. It's not transferred. It's shared. It's shared by the 2 nuclei of 2 atoms of either the same or different elements. Mostly, though, even there are different elements, they still belong to the same category we call what? We call the electronegative elements, which most of the case for covalent bond formed by those elements in the non-metal area. Now, even though they were considered electronegative, but they have the electronegativity value slightly difference between each other. See those difference? From boron's 2 all the way to fluorine's 4.1 or 4.0. And it's almost half. 2.5, 2.3, 3.5, and 4. And then going down almost the same, like a 0.5 difference between the value of electronegativity between two different elements. So they have slightly difference. So the difference of electronegativity from two different elements in that region can still be forming bonding slightly or slightly difference when the difference between the electronegativity value and then form some kind of close to covalent but still have a little bit ionic nature. Now we're going to talk about this as a third kind. Now the first kind we talked about those elements, right? For instance, hydrogen, and those diatomic molecules, they made from the atoms from exactly the same element. For instance, hydrogen. Right? Hydrogen is a diatomic gas molecule in nature, H2, right? And there's a couple others like chlorine gas, Cl2, right? And then you have oxygen gas, O2, and nitrogen gas, N2. Of course, they may involve not only single bond, may involve double bond, triple bond. For instance, nitrogen gas has a triple bond, and oxygen gas, it has double bond in between two atoms of oxygen, or the triple bond between two nitrogen atoms. But what is triple bond? We haven't reached that yet, but we can give you small exposure, right? We always prefer to give you exposure. The triple bond or double bond, they just have the electron inside those atoms getting close enough. If it's head-on from each other, those will be considered as sigma bond, single bond. But if you head-on close enough, you consider two Cartesian system, right? Two Cartesian system, H, Y, Z, as a Cartesian system. And you have a single bond close enough to overlap the electron cloud. That is a sigma bond we call single bond. But if you have also electron in those two other coordinates, and when the first XX overlap form single sigma bond, but if you don't have electron, that's fine. If you have electron on this coordinate and this coordinate, and then the three coordinate Cartesian system, if they have electron, they're getting close enough, they have interaction between those electrons sideways. So they seem to have electron interaction between these two axes. And then look, if you have these two with a bar on top of it, right? With a bar on top of it, does it make a pi? Does it make pi? Right? Does it make pi? So you have two pi bonding to make the three bond slightly different in the bonding energy, right? The strengths, the lengths, but they are considered a triple bond, right? In this case, they are considered triple bond. So nitrogen have triple bond, oxygen have double bond. We will get in there in the future, but those bonding also can be shared by the bonding electron can be shared equally by the two nuclei from two atoms of identical, the same element, right? Oxygen, oxygen, nitrogen, nitrogen, hydrogen, hydrogen, chlorine, chlorine. So they're supposed to have 100% completely shared, equally shared, oh gosh, equally shared bonding we call covalent bond. So in this case, that first covalent bond we have definition right here. So let's see if we have example, right? Example is let's say use hydrogen gas. Hydrogen gas is a diatomic molecule, right? With a single bond, single sigma bond, right? Between what? Between the two nuclei of hydrogen atoms, right? hydrogen atom. The two hydrogen atoms, they are identical. They are exactly the same, and which are 100% identical, right? In their chemical character, right? So what happens? So the single bond is the results of what? The results is the results of 100% equally shared, right, bonding electrons. Right? Shared bonding electrons. So that is the 100% covalent. So it is 100% covalent bond. So in this case, what happened actually is this. We try to give you some idea what the energy level, right? The hydrogen gas, the two hydrogen atoms involved, and then you have these two atoms getting close enough in nature. Now we don't have too many hydrogen atoms, single atoms floating around in the atmosphere because that's not stable. They consider as a zero energy they possess if they can stabilize in the atmosphere in nature, but they are not, literally there are not many possibilities for them to stay there by single atoms. So what happens? What happens is when they're getting close enough to form bonding, right? For a single bond, that's covalent bond because they share, the electron be 100% shared at equal distance because the atom of hydrogen atom number 1 is exactly same as hydrogen atom number 2, right? They are same element and then same atoms, identical. So none of each is stronger than the other to pull the bonding electron towards itself. So they have a tug of war between these two nuclei. One says, I want those two bonding electrons close to me. And the other says, no way. I'm as strong as you and I'll pull over. If you pull over towards you, I'll pull back. So finally, the argument, the battle was stopped. Said, oh, okay, nobody can win, right? Nobody can win this competition. So let's not compete. Let's just share them in exactly the middle of us. Let's both share their existence to hold us in between, and with certain distance form a molecule which has two atoms, and with one single bond with electron clouds overlap. So what is the distance? That's the distance between the two nuclei, and then of that single bond, that's called bond lengths, right? So what happened to the energy? Now, if you have seen that picture, if you have read the textbook, not many textbooks still have this, but I think I have. Remember, if you have energy and the bonding links, right, a relationship, the diagram, it looked like this. If you have the vertical y-axis, right, y-axis as energy, it's bonding energy, right, bonding energy EB, all right, and then you have this, and you set right here as a zero, like ground zero. It's a stabilized ground zero as the origin, and you go to the horizontal axis as the bond lengths, which means the distance between the two nuclei when they're getting close, all right? What energy to the system between the energy value involved in this system was two hydrogen atoms. Now when they are far apart, when this hydrogen and almost has no relationship with another hydrogen atom, right? Each so far away, the energy level for either one of them is close to zero. But That's not the most stable lowest energy. But when they're getting closer, right, getting closer, then energy seem to be give off and getting lower for this whole thing as a system, diatomic. But then getting to a certain distance, right? Certain distance. This is not zero. That's two little circle represent two atoms, right? That's hydrogen. That's another hydrogen. Another hydrogen. Now they have a close enough region to form a bond. That single bond right here, the sigma single bond right here, sigma bond right here, and that's another hydrogen. They become a hydrogen diatomic molecule. Right? We do not call compound because only one element. And then the energy level of the whole system with two hydrogen atom had a certain distance. At that particular distance, the two nuclei suppose repel each other away from each other, and now the bonding electron, the bonding electron pair coming to in between them at the same equal distance between the two nuclei, and then has attraction towards positive charge, electronegative charge, right? Towards a positive charged the proton of two hydrogen atom, which is the nucleus, right? And then, so the nucleus supposed to be pushing each other because the proton all positive charge, they have repulsion. But now the electron get in the middle, and the electron says, don't go away, let's get together. So the electron pair attract these two nuclei closer to a certain distance where the repulsion between the two protons is minimized to minimum, and the attraction between the proton and the electron also reach the minimum. That is the case, the whole system, the energy level for the whole system when the two hydrogen atoms combine into a single bond at a fixed certain distance. What is the value? I think it's about 0.74 nanometer, I think. Nanometer. That's the distance. So that is the distance for the bonding between two nuclei of two hydrogen atoms. Then that is the hydrogen diatomic molecule form a molecule. But then if you keep on going even closer, so if that's the case, if the two are getting too close, then the repulsion between the two nuclei or two protons will be much, much greater, stronger. Then the energy level suddenly shoot up, goes to the roof. How this is going to be look like this. So this time, this close to, so what is this? This is the difference for the energy of the system. At this length, the difference between, the distance between two nuclei, which is about 0.4 or 0.7, I think 0.74 nanometer. I think it's 0.074. I think it's 0.074. 0.074. 0.074. If I remember correctly. 0.074 nanometer. And it was 74 picometer. And there's sub angstrom. Angstrom is a nanometer. That's the angstrom. A was a circle on top. That's a sub angstrom. So, and then this distance. And then that will be the most stable, because the whole system has the lowest energy. That energy difference, delta E, right? Delta E is about minus 489. Oh, let me erase this. This was too close. The delta E is the difference for the energy reduced for the system going down equals minus 484, is that right? Kilojoule per mole. Each mole of hydrogen diatomic gas molecule were released. That neg means what? Exothermic, right? We talked about exothermic, endothermic when you were in middle school, high school, but you did not know it exactly. The exo and the endo has something to do. We're gonna get in that for a 2-hour introduction about thermodynamics, about energy and the system surroundings and energy spectrums. We're gonna talk about this, and then in very short period, that's one chapter in textbook. But here we talk about negative sign. Negative sign means what? Losing electron. Losing electron from what? Losing electron from the system. So the system has more electron before they combine into the single bond. When they become bond and they get lower electron, they lose that negative. It's the value lost, all right, the energy. So this is the diagram for energy and the bonding. So you form a bond, even if covalently shared equally between two nuclei, but the energy level go down to lose more electron, getting more stable for the molecule instead of for atoms, right? So now, if you don't understand this, let's give you some kind of hit home, simple analogy in the routine life, right? In the routine life, if you want to break something, for instance, you want to break a pencil, right? You'll break a pencil, and do you have to snap the pencil? You snap the pencil, broke into two pieces. Do you have to put energy in there to do so? Yes, you have to put energy into the pencil to break, right? Now, if you go backwards, thinking backwards, if the pencil, we already mentioned this example in the past, I remember, and if the pencil is able to automatically recover by itself, the two pieces become like a magic, those cartoon character or cartoon movie, in Disney, right? And then all these become a magic, and the pencil, the broken pencil, become one piece. Now the energy you put in to break the pencil before it becomes two pieces, that energy, according to the law of conservation of energy, it doesn't go anywhere, right? The energy cannot be destroyed nor created. Can only be preserved and stored in different form, or preserved or transferred between different forms, right? Converting in between different forms. So the energy you put in to break the pencil, if the pencil is able to repair itself back to one single piece, the energy you put in will be completely 100% returned to the space in different form, right? So that's the same token here, like you consider two hydrogen atoms as two pieces of broken pencil. You put energy in there to break them down. They're stable, they're unstable. But if the two pencils can automatically go back to itself, form a diatomic molecule, the energy you put in to break them apart, it will be regained, recovered, and emitted back to space in the different kind of form. So in this case, it's the system of two hydrogen atoms losing some energy when they form bond. The bond energy will be released to space with different form. So that is the exothermic with a negative sign, negative 489 or 484 kilojoule per mole. In other words, 1 mole of hydrogen gas, right, coming from 2 moles of hydrogen atoms become 1 mole of hydrogen gas. Am I right? Right? 2H, right? H plus H equal H2, right? So 2 mole hydrogen atom, and then give you 1 mole of hydrogen diatomic molecules, and the energy will be released to the space and in a exothermic process, right? That's what negative is. All right, so that was more stable. So you form diatomic molecule, hydrogen is more stable. All right, this is a situation we understand now. Now in the covalent bonding area, this is extreme because why? These two atoms from the same elements, they are exactly same atom, they are exactly 100% identical. So the covalent bond will be considered what? 100% identical chemical characters. So the single bond is what? Is a result of 100% equally shared bonding electron. So it's 100% covalent bond. But there is a situation in between. The one extreme is completely different. They share the electron, or they not even share the electron. The one electron transferred from one electropositive elements to the electronegative elements, right? That's called ionic bond. Then with covalent bond, 100%. So the third kind is in between. The third kind is in between. Third kind is called polar covalent. Polar covalent bond, right? Now, here we can also put out here, if the difference, we talk about the hydrogen, right? The hydrogen gas, the difference for chi, what is the difference for chi? In hydrogen diatomic molecule case? You tell me, right? What is hydrogen electronegativity value? 2.1, right? So the delta chi for what? Delta chi for hydrogen diatomic molecule, right? So it's going to be what? 2.1 separate 2.1 is going to be what? 0, right? So that is very, very extreme. They don't have any difference between the electronegativity between two hydrogen atoms. Of course, they are identical. So that is 100% covalent bond. But then the polar covalent bond, then we are able to figure out if we talk about the bonding type, ionic covalent or polar covalent. The polar covalent must have a electron pair for the bonding electron pair being not 100%, partially shared by two nuclei, right? It's going to be, the electron pairs are going to be pulled over by one element. The atom from one element has a little bit higher electron negativity, and then the other counterpart has a lower electron negativity, right?